Yeah. Cool. Kia ora everyone. So as Trevor mentioned, Heather and I have been looking into methods to measure residual / volume in New Zealand's erodible cutovers. So first we will go through the problem, define our project objective, go over the methods we investigated and the results of these, and then talk about our recommendations and our conclusion. As I'm sure you are all aware, slash mobilisation has the potential to cause serious issues to both the environment and also to forestry social licence. Risks of slash mobilisation have been increased with severe weather events like Cyclone Gabrielle. Therefore, the NESCF have imposed changes to encourage more sustainable forestry practices and to mitigate the effects of mitigate the effects of slash mobilisation. So a new condition has been added, which states that you are only allowed to leave 15 cubic metres of residual slash on the cutover in an orange or red erosion susceptibility classification zone. This refers to pieces that are over 2 metres in length and which have a large in diameter of over 10 centimetres. As this change targets steep slopes, there is an opportunity for remote sensing methods. However, we discovered that there was significant investigation to be done with these methods. Therefore, the objective of this project was to investigate both remote sensing methods and ground-based methods by trialling them on a recently harvested cutover in an orange or red ESC zone. What we mean by a defensible method is one that is accurate, precise, repeatable, and preservable, as well as being compliant with safety standards. In terms of a practical method, this is one that is feasible on steep slopes, can measure residual slash per hectare within a practical time frame, and that uses equipment and knowledge readily available to the forestry sector.
So we trialled 3 methods at a site that had been harvested in April and was in orange ESC zone. So firstly, the ground-based line intercept method. This is a well-established method. You might have heard it called Wagner waste. We tried 2 remote sensing methods. Firstly, the same line intercept procedure, but in the photogrammetry point cloud. And secondly, a machine learning / detection on the orthophoto. So the line intercept method involves defining a line of interest. We use 2 25-metre transect lines at each plot. For each slash piece that intersected with the transect line, we measured it if it was over 2 metres in length and had a large end diameter of more than 10 centimetres. Then the volume at each plot was calculated from the diameter at intercept and the length of each plot. And we marked the end of each transect lines as well as every piece we measured with spray paint, so we were able to find it in the orthophoto. To get this orthophoto, we flew the block with a ground sampling distance of about 1 centimetre. We could see the spray paint in the orthophoto and use this to line up where the transect lines we measured on the ground were, like you can see in this top photo. Then the same measurements were taken as per the ground-based line intercept method, but by manually manipulating the photogrammetry point cloud. We worked with Interpine, who ran their machine learning model on the orthophoto, which detected slash pieces across the cutover. The volume of each slash piece was calculated from the length and average width of the detected polygon. Then the volume of pieces longer than 2 metres was used to create a volume surface. However, you'll notice this split here. So an issue with all machine learning models is that due to processing constraints, you've got to split the orthophoto into tiles, and the boundary of these tiles might fall in the middle of a slash piece. So we did some post-processing in ArcGIS to combine pieces if they were close to each other and orientated the same way. Then we added the volume of all of the pieces that intercepted with those transect lines that we found in the orthophoto earlier, which meant that we could compare to the volume of the ground-based method.
Awesome. So we're just going to go over our results and discussion. So this graph here shows the volume comparison between the ground-based and photogrammetry baseline intercept methods, and this was across 25 different plots. So on average, the ground-based measured 31 metres cubed per hectare, while photogrammetry consistently reported lower volumes with an average of 13.6 metres cubed per hectare. The significant variation in the ground-based method of plus or minus 10 meters cubed per hectare could lead to over-removal of slash in order to meet compliance. This highlights the need for careful method consideration in order to balance both environmental impact and compliance. Here, the same results are displayed in a scatter graph, so you can see the relationship between the two methods. The R-squared value of 0.61 indicates a moderate strength of correlation between the two approaches. You can see there is a consistent underestimation by the photogrammetry method, as most points fall below the line of equality. Photogrammetry measurements at lower volume plots align more closely to that of the ground-based method, with discrepancies growing in plots of higher volume. This shows that photogrammetry is more efficient in regions with lower slash densities, where the likelihood of obstructed visibility of the measured pieces is significantly lower. To understand where these discrepancies came from, we matched each piece found in the ground-based method to that in the photogrammetry method. We found 119 pieces during our ground-based method, however, only 57 in the photogrammetry analysis. It's important to note that each piece found during the photogrammetry analysis was found during the ground-based method. So this is just a pie chart illustrating the reasons why certain pieces were not included in the photogrammetry analysis. So the main issue we identified was that many pieces were buried or partially obscured, making them invisible in the photogrammetry point cloud. This highlights a key limitation in optical remote sensing, as if a piece is buried, it may not be able to be measured, leading to an underestimation in the overall volume of slash. We also found that 21% of the pieces identified during the ground-based method, but not the photogrammetry method, did not actually intersect with the transect line, as you can see here in these images. This was primarily due to challenges in maintaining a straight line across the difficult terrain, leading to an overestimation in the overall volume of slash.
The machine learning creates a wall-to-wall volume surface shown here. The average of the volume across the cutover was 14 meters cubed per hectare, which is pretty similar to that measured by the photogrammetry method. Importantly, some of the highest density areas identified by the machine learning had no plots in them. So without the machine learning wall-to-wall method, these areas would have been missed. The spatial information you get about the slash density is also useful if you want to look at slash volume on specific landscape features, like in gullies. This graph shows the volume calculated at each plot from the pieces detected by machine learning compared to the volume measured on the ground. You can see there's quite a high variation between the two, with a moderate to weak R-squared of 0.39. This is quite similar to some other studies that have used machine learning to detect woody debris volume, such as Udali in 2023 found an R-squared of 0.31, and Windrum in 2019 found an R-squared of 0.57. So interestingly, both the model we use and those models used by other studies have quite high performance metrics. So that means that the models are very good at detecting slash within their own training data. But then when it comes to a ground truth of that volume, they're a lot less accurate. So this means that for any machine learning method, it is critical to ground truth the volume in order to understand its actual accuracy. However, even with this lower accuracy, there's clearly a positive relationship supporting that machine learning can be used to find the high density areas.
So to measure residual slash in New Zealand's erodible cutovers, it is essential to match the method to the site conditions and the purpose. If you want an effective and complete assessment of slash, a hybrid approach is recommended, starting with machine learning to identify areas of high slash density, where the advantage lies in its ability to assess the entire cutover without solely relying on plots. For these higher volume areas, the ground baseline intercept method can be employed for an accurate volume estimation, where it's particularly good where pieces are partially buried or obscured. For low density areas, photogrammetry is a more efficient and safer option, as it can cover the cutover quickly, and is good where pieces may be less likely to be buried. In situations where timely decisions about slash are necessary, such as when a harvesting crew is relocating equipment, a visual approximation of slash may naturally be undertaken. However, this is often inaccurate and lacks repeatability and preservability, underscoring the importance of not solely relying on visual judgment for slash management.
So to summarise what you've just heard, we investigated methods to measure residual slash on New Zealand's erodible cutovers, balancing practicality, accuracy, and defensibility. On our study site, the ground-based method measured 31 metres cubed per hectare, which was a slight overestimation due to difficulties in the steep, complex terrain. The photogrammetry method measured 13.6 metres cubed per hectare, which was a significant underestimation due to the buried pieces, though this was less important at low/density areas. The machine learning method measured 14 metres cubed per hectare, which had quite a weak correlation with the ground-based volume. However, it was promising for initial assessments. Combining these methods offers a balanced approach for forestry. This study contributes to the ongoing conversation around sustainable forestry practices, emphasising the need to align measurement techniques and regulatory frameworks with evidence-based risk reduction and community expectations. This is key as we navigate the future of forestry in New Zealand as we strive for sustainable solutions that protect the environment and the interests of local communities. Here are our references. Thank you for your attention.